Okay, welcome to today's class on from 6950. Thanks very much for accommodating me on Monday and just watching some videos and some content. My internet network issues, that's what I was able to do. The same content though. So I think we've now covered a lot of the core topics that I want to cover in this course. Among other things, in the material that I released on Monday, you would have seen a description and an announcement of assignment number 8. So what you should be working on right now, many of you are working on or just submitted assignment number 7 as of today. That's great. Sometime over the next week, hopefully you can get an assignment on pandas completed, assignment number 8. And I think that can conclude the assignment portion of this course. Like, you can always do more, but that's plenty. That's tons. So up to now, we've had an assignment every sort of class, and you've been working through giving you a minimum set of skills to be able to work in a computational environment. I've still got a handful of other topics I want to go over: data structures, file formats, databases, high performance computing. Maybe a few other things, but I won't do assignments per se on those topics. What we're going to do is we're going to switch to the sort of the last half or third of the course to a more project-based scenario where you'll be working on some code using these skills, but you can think of the project as being the equivalent of like 3 or 4 assignments. So in terms of scope of work, think of a project as being a multiple assignment kind of thing. So the assignment from now on is just the project. So a lot of today will be about getting into that project and explaining what I'm looking for and getting started on it. But before we do that, let's take up what I called assignment number 6. So this was the third component in terms of an introduction to Python. What I've been doing throughout this course, I'll just share an entire screen so you can see what's going on here. What I've been doing is just tracking for each one of you whether or not you have spoken in class regarding an assignment. And you can see how a few of you have a grade and a few of you don't have a grade. And when I mean grade, this is like a really low bar. It's just pass or fail, like you did it or you didn't do it. That's all I'm looking for. So if I could get 2 volunteers for day, one person on Slack already said yes. Is there someone else here who is not yet gone? Maybe Kabir, I see on the channel, and I don't have a mark for you. Would you 2 be willing to talk about your assignment number 6?
Yes.
Excellent. Okay, so if you would, it's always helpful to turn on cameras so that if you're willing to do that, so the class knows who you are. And then who was the other person? Okay, help me out. Rushin.
Professor?
Yes,
can you hear me?
I can. How do you pronounce your first name?
Racing.
Racing. Okay, thank you. Awesome. Perfect. I've got two people willing to stand up and talk to us a little bit of assignment number 6. I appreciate it so much. Okay. So I think the easiest thing for me to do, just to keep the screen shared, is I'll just jump over to GitHub here, and this is one of the reasons I keep everything in the grade book. So I should be able to fairly quickly look up. So we have a GitHub username. That's perfect.
Yeah.
Okay, so there's your GitHub account, and then the other person. Said it helps me from spelling it incorrectly. I don't think I'm showing any grades. There's your GitHub. Okay, so now we got something to work with. Okay, so you have done a little bit of stuff on GitHub, but specifically we want to focus on practical Python and what's in your work directory. And then for this one, practical Python and what's in your work directory. Okay, so what I want to do is just address a little bit of the stuff that was covered, and my memory is most of the exercises were either in report, PCOST, or file parts. So let's just start with the report.py and sort of go through some things that you see in it. Okay, so one of the big changes here was the idea of modularizing your program and turning it into a function. So there's a lot of things going on here because we did several exercises all together. So I'll start with some of the easy stuff. The stuff at the top here. So what do those 4 lines do in this code? What's the purpose of them?
Okay, so the first line, I mean the line 6, it defined a function called make report, and the parameters is the portfolio and prices. It's a file name. Need to pass in this. It's a file name. I need to search. I couldn't remember. It might be the file name to pass in this function, and the line 7 to line 9 is the description of the function. So if we type the help make report in the command line, it will show what the functions do.
Okay, so you know how you just said portfolio and prices, I think that's the file name, but I don't remember.
Yeah, I couldn't remember.
No. My point I want to make is that's exactly what this descriptor is supposed to help you with. Right. So rather than like your description of the function make report is make reports. So if I didn't know what this function did by its name, this doesn't add anything to it. It doesn't help me understand what this function is. What this description, this doc string could do is explain, what do you mean by portfolio? Portfolio is a CSV file containing a list of prices, or a list of positions. Prices is a CSV file containing a list of stocks. This function returns, well, that's what we should have up here is what the function does, right? So at the end of this routine, what does this function return? What's its what do you get out of it?
Sorry, Professor, can you repeat again?
What does this function return? What's its like when you call make report, what's supposed to come back?
It returns a list of reports.
It returns a list of reports. Okay, so that's where it gets a little bit tricky here. Is it seems like this function is doing 2 things. It prints out the header of it. So this function prints stuff out, but it doesn't print out the whole report. It just prints out the header. And then it returns a data structure, including the data associated with it. So this is a bit of a mixed function, right? Where I call make report, and it's got the side effect of printing some code out, and then it returns a data structure.
Yeah.
Right? I would have reworked this, and I can't remember what the exercise said, but I would have worked that so that this information was part of this data structure.
Mm-hmm.
So that when you called another function, print report, what this print report would do is the report would have all of the data required to actually print out the report. And specifically this is part of the report, right? This header information, that's part of the report, right? So do you see when we're grouping up pieces of code, we want a function to do something, have minimal side effects, and the doc string should explain what it does, right?
So yeah, so it might be better to move the print header part to the print module and okay.
Yeah, I would recommend. No, I can't remember what the exercise told you to do. If the exercise told you to do this, that's fine. But as an improvement, I would have done that. Okay, so that's great. Thanks for the explanation. Let's go over to here and let's see if we can find anything else in report.py to talk about. Okay, so same comment here, Kabir, in terms of the comment. Do calculation and make the report. It doesn't really explain what that means, right? So this isn't enough information to explain what this thing actually needs to do, and it doesn't explain what portfolio is, prices is, or what report is. But I can see that you have, when you printed the report, you actually have the headers inside that function. That's fantastic. Okay, so let's talk about in your code this function right here. Read to files and call other function.
Yes.
So
okay, this function do just this function calls another function
yes,
to make the data set.
to make the data set. So so the portfolio is the data set, right?
Yes.
Prices is the data set.
Yes.
And then you need to call make report, but I see it's commented out here.
Okay. For some reason, I just before the last comment, I just commenting this one.
Okay. so this won't work as expected, right?
Yes.
Okay, I understand. Okay, so that's just something to hear about. So this line right here, this print, do you think that's a is that actually put in your code, or is that a debug message?
No. Just to say you that when I commenting this, I was checking that what is the portfolio returns, and this was my last comment.
Right. Okay. So you accidentally had a debug message included
Yes.
included in there. Okay.
It should be commenting the print one, and the report should not be the commenting one.
Okay. I understand. So the way you've written this, what read file is doing is really, this is your main routine, right? You read in the portfolios, you read in the prices, you make the report, and you print the data.
Yes.
This is the main function. So what you have here is you have a function called main that calls this thing. If it was me, I would have just taken these 4 lines and put them right here. Okay, because it doesn't really add much. Like it does a little bit, right? You have a file name and a file name, right? So you parse the files, but that doesn't really do a heck of a lot. What I probably would do is have this thing be called main, and then this bit of code that handles the command line arguments, I would actually push that into here, like into this routine.
Yes, in that case, we don't need the read file function.
No, because it has to do with reading code, right? So I have to go from here to here to here to here to here. I got to go that many steps deeper into the code to figure out what's going on. Okay, that's great. So we're just sort of talking about different ones. Okay, I'll ask you a different question. Let's go to file parse. Okay. So file parse is something you added for this exercise. Okay, it's a module. Okay, so that means that it has no command. So if I was to write just Python space file parse.py, what would happen?
Okay, it will show error. Oh, no.
So if on the command line, on the command line, if I was just to write Python space file parse.py return, and that's it. What would happen when you ran this module?
whenever you call, there should be some parameter.
Oh, okay, I'll try it one more time. If you were to, on the command line, say Python space file parse.py and hit return, what would happen? What code would be executed if you did that?
The main code, the main function.
No. If you said Python space file parse.py, this script would define parse CSV and then end. It doesn't do anything.
Okay. Oh.
Okay. So that's the idea of a library, right? So it has no main, right? So it will run, but all it does is define parse CSV and then exit. Sometimes, because as you're developing this code, you need to test this function, right?
Yes.
Sometimes what people do is for these scripts, they put in an if name equals main portion and put the test right in there. So you can sort of leave the testing code in these kind of scripts when you need them. You don't have to do that, but you can.
Okay. Okay, I understand.
So the other comment I'll make on this one is this thing right here. So let's just read what this says. You have this function that says parse CSV, and it says parse a CSV file into a list of records. Okay. So this gets a bit tricky. Does the argument of this function take a CSV file? Is that the input to this function?
No, it's like it's just a comment I wrote, but it should be the parameter details.
What do you mean by the parameter details?
For example, what kind of lines and select, what is their details,
right.
And I should.
Okay. You know what? I'm not worried about all of these, but the really important thing is you said parse a file. So this would tell a runner of your code that you're expecting a file handle or maybe a file name, but in fact you don't want either. What you want is a bunch of lines. So this is a little bit strange, where you just need to be clear. So what I'm getting at here is writing better, longer programs. So as programs start to have multiple functions and multiple modules, it's that much more important to actually get this stuff right. It doesn't really matter what goes inside here. Like, it's got to work. But when you're working with larger and larger codes, this is actually what everyone reads. Like, I don't read this. I read this. And I assume that this code will do exactly what it says. Okay, we'll flip back here. I'll ask like 2 more questions, and we'll be done here. So let's go to your file parse.
Mm-hmm.
Okay. Nice. Now look at this. So you handle whether or not lines is a file or is a bunch of lines. Much better documentation. Okay. So my question here is, I thought you raised an argument. So this file parses any CSV file. Oh, okay, here we go. What is line 21 and line 39? What does that do?
For the line 21, if the has header is true, if the has header is false, I mean, if we give the file that doesn't include the headers, and at the same time, if the select is true, I mean, at the same time we pass a parameter, we give the select list when call the file, when call the function.
Right.
Yeah. At this condition, the program should raise the runtime error, because if we only have the select list but don't have the header name, we don't have a file header, the select won't work. So That's what the line 21 works in.
So no, I understand that the purpose of this block of code, but what I'm trying to get at is what does actually this do? What is a raise runtime error? What happens?
It will print a
When
line in the command line, and
so no, it does not print a line on the command line.
Okay, Professor, is this
Yeah.
this line like exit the Python code whenever user does not provide a header name?
yes.
No, it will not exit the Python code. Okay, and this is where I want to make it clear about what you're doing. You're not exiting the Python code, because there are system calls which will exit the program. There are lines which will print warnings to the thing. You're not doing either of those things. What you're doing is you're raising something called a runtime error, which is a kind of exception. So I'll ask the same question here. If this code, inside this code, there could be a raising an exception. It could raise a value error, right? If I raise a value error, I might get something printed to the screen. I might have my program end, but it doesn't have to happen, right? What can you do? You can catch that error.
Yes.
Okay. So in the same way that when someone calls parse CSV, right, a function calls parse CSV, I could capture runtime error, right? And so it doesn't print it out. It doesn't stop the Python program. It just raises an exception. And if that exception gets all the way to the top, well, then you get the error message. But it doesn't have to print that out.
But I remember it prints in the
It
interactive
does,
mode.
because you aren't catching the exception.
Yeah.
Right. So there's no guarantee. So if you were to write a program that called parse CSV that did a try around it, you may never see this warning.
I remember I saw it.
So no, sorry. It depends on how you call the program.
Yeah.
Right. So you don't, like, you'll see it if you call this function directly, but other user might use this and get this runtime time error. And if they put a try except around it, just be clear that it doesn't always end the program or always print something out. What it does is it raises an exception that some higher level part of the program, like you've done here, makes it go. Because if you did value error and then silence error, right? You could hide that, so it never appeared.
Yeah.
Right. Cool. Okay. Just want to talk about what those exceptions are, because you'll see those in Python code all the time. Okay. Let's just go back to the other one here, and we'll find one more function, and then we'll move on to something new. Let me see if I can find. So you have. Okay, so this is PCOST. Oh wait, this is actually 1.27. This is the other problem, right? Oh, this is where you're reading in a module. Okay, let's talk about this for a second. Okay, so you've got this function PCOST, and so this is going right back to the beginning of the exercises. You import CSV as a module. You import report dot module, but report, doesn't it read in a portfolio and read in a prices and make a report? How is report being used so that you don't have all the code executed? I'll remind you what your report said again. Your report has print data and make report and read file and all these functions. When you import report.py, is the report.py script run?
Yes, Professor, when we import the file, then with that name, we can call all the function of that file, that namespace.
Yep.
For example, report.
Yep.
And then here
you can call the function. Yeah, and then you can call that function.
Yes.
I understand that, but my question is, does the entire script report.py get run? Will you see a portfolio report appear on the screen?
Yes, whenever we import, then all full script of report imported here, and then whenever yes.
Okay, so not quite, right? Because if you look at your report, right, you define all these functions, but you only ever call main if report.py is the main routine. If you import report, then this never gets run. If this never gets run, then this never gets run. If this never gets run, then this never gets run. So if you just say import report, nothing will happen.
Okay.
Right? Do you see the difference there?
Yes.
Okay, so this is the idea of a sort of a script versus a module. So a module or a library has functionality, has these functions like read portfolio, right? But
yes,
they don't always do it. In fact, this module is importing another module, right? So you have pcost imports report, which imports file parse.
File parse, yes.
Now we're getting into sort of a more realistic piece of code that has all these parts to it. That's very, very, very normal. I got one last question for you, which
yes.
is right here. What's a system exit?
Okay.
What is this?
System exit. Okay. If there is no argument, like if the argument is less than 3, then it will exit a message, exit with this message.
Okay. So is system exit an exception?
It's something like just you showed previously. It shows a user understandable message.
Okay. Well, it's showing the usage string. Okay, but that's not always used with a system exit, and this is what I'm not entirely sure about, and I'm wondering if you know what a system exit does. It has to do with how programs are called. Like one program calls another program.
No, Professor. Whenever I provide less than 3 parameter, in that case, it shows that it is error message.
Okay. Okay, so it's a low-level feature. So what I'm doing is I'm reminding myself of the subtle differences between system exit as an exception and sys.exit, which returns a return code. Every program you run on the command line has this idea of a return code. It's a number between 0 and 127. And it's not just a Python thing, it's all command line programs. And the assumption is if the program worked correctly, the program will return a 0. This is like in Bash, it will return a 0. So what a system exit is doing is returning something which is non-zero and printing this out.
Yes.
And so the subtle difference has to do with where the message is being printed out. So this is actually being printed out, not to standard out, but it's being printed out to standard error. And so my only hesitation is whether or not you'd want documentation to go to standard error or to standard out. It's the subtlety, but it's slightly different. For simple codes, it doesn't make any difference. But I sort of was curious on where it came from. Okay, anyway, that's done. That's great. So what we've covered now, thank you very much for the two of you. I appreciate it. I will go along and very happily, see now I can do this. I can go class participation. Fast. There you go. You have made a class participation. And I'll do the other one. And we'll go and talk about the project now. So I'll just do the same thing here. I'm just doing this because if I don't do it right now, I'm going to forget. Assignment participation. Yay! Okay, perfect. For the rest of you, if you have not yet made a contribution in class and you know, shown your, talked a little bit, I am looking for you. We have 2 more assignments. So if you are in this list and you don't have assignment presentation, especially if you're watching this in the recording, but please try and come one of the next 2 days so you can talk about either your assignment 7 or your assignment 8, so I can give you a nice little check mark. But anyways, we'll get to that. Okay, I want to talk about the project. Okay, so last night I was doing some typing and writing and trying to put my thoughts down. And in the Slack channel, I posted this little message right here. And I said, I've written up the scope of work for this project component of the course, and I gave you a link to a GitHub project. Okay, so let's go to that GitHub project and take a look at what I created here. So I'm posting the project itself as a GitHub repository, okay? And that's just a way of me pushing files or doing whatever. And I've got a few things in this GitHub repository. One is I have a little README file, name of the course, and I've got 3 links that we've got here. So let's start. And if you read this already, this is great, but we'll talk about it all together. The project instructions. Okay, what this is the capstone project. I'm trying to link together some of the ideas we've been talking about and give you an example of what doing computational science with the tools we've been talking about would actually look like. Okay, so it's due the last day of class, so it's due in 2 weeks. Now, remember that this course, we're doing 2 long classes a week. It's only a 6-week course, so 2 weeks is the equivalent of an entire month in a regular course. It is equivalent to every assignment from here on out, and it's the last day where I need this done because we're going to do some presentations and peer evaluation on it. So start working on it today, work on it for the next 2 weeks, but 2 weeks from now, we're taking this up. So plan your time accordingly. Okay, so here's the background. When you're doing computational science, and today, more and more science is computation. You involve computers in some way to actually get your scientific results. The common scenario is at some point, you or someone else are going to develop some software. We're going to write some code that solves a scientific problem, or does some data analysis, or does some processing, or does some machine learning algorithm, or does something, right? There's always a part in your day-to-day life, which is writing code, scripts, applications, as part of doing computational science. Once you have that program or script or library or tool, whatever it happens to be, very often you need to run that piece of software under various conditions, right? You might run them with different input files. You might run it with different parameters. You might run it at different scales, little data, big data. You may run it many times on lots of different data. You may run it just once, but it takes a long time to run. It depends on the problem, but you have to run that software under various conditions. Now, if the problem isn't trivial, if it's not a piece of code that's like really quick to run, almost always when we're doing a scientific problem, you actually need a decent computer to do it, right? This is why we have high performance computing and computers with hundreds of CPUs. Not always, but often a computational task has some expense to it, some cost. And so when you run your software, whatever it might be, you probably want to store the output of your model or your scenario in some intermediate file, okay? Now that could be a text file, a CSV file, a data storage like a SQL database. It could be a bunch of image files. It could be a binary file format like NetCDF or HDF5. It could be some file format which is specific to your discipline. And it could be some original file format that you've come up with. Often there's a step where you create something and you save it to disk. once you've got your data, we'll call this output from the model intermediate data, right? So you might have some raw data from an instrument, but you've got some data, you've done some processing. One of the steps you do is you want to take that data and then build visualizations around it. You want to open that data, that intermediate file is up, and because it's binary data, you can't just look at it. You've got to build some sort of visualization to do your science. Now, this could be a chart, a figure, a plot, could be a table, could be some other sequential step in a software pipeline, but you got to do something with it. But often, visualizations, charts, plots, graphs are one of the ways we use to interpret the output of these steps. And then part of doing science is communication, presenting your results, publishing your results, making a poster of your results, putting up a web page of your results. Some way you got to communicate that. And so I think at some level, we can break down many problems, computational science, sort of into these categories. So for this project, what I want you to do is I want you to pretend that you are a researcher, a relatively new researcher maybe, in some computational science domain. And it doesn't really matter if you're an expert in this field or not. I actually don't want you to choose something you already are an expert in. So if you're taking this course and you are an expert in machine learning, don't do something in machine learning, do something in astronomy. If you were an astronomer, don't do something in astronomy, doing something in seismology. If you're an earth scientist, don't do something in seismology, do something in oceanography. It doesn't really matter, but the point of it is to do something in computational science and demonstrate that you have mastery, or at least the beginnings of mastery, of doing these things. Okay, so in our imagination, let's imagine that at a conference that you recently attended, you saw a presentation from some other research group that you thought was really cool. Like it was in your field, but you're new to the field and you're trying to learn about it, and you want to try and reproduce some of their work, okay? So reproducibility is one of the themes here of this project. Now, fortunately, that group is practicing what's called open science or open source science, and they published their results or their software in something called the Journal of Open Source Software. Okay, so here goes step one of this project. What I want you to do, and this is something we'll start today as a group, but you can continue this on, is I want you to choose a topic from a list of these Journal of Open Source Software papers. Okay, so the Journal of Open Source Software. Let me take an aside here and explain what this is. It has been recognized that as science becomes more and more computational, using papers, as in scientific papers published in the peer-reviewed literature, though it does capture the output of some scientific work, is missing the contributions of software developers, data engineers, software architects, and a lot of the actual effort and work we do in doing science, because the work isn't answering a scientific problem, it's developing a tool, an application, a library that has a lot of utility and a lot of impact. And because a lot of science is evaluated basically on citations, if you write a great piece of software, how do you get academic credit for it? Well, the way you do it is you publish a paper. So the Journal of Open Source Software is one of a number of journals which have come on board in the last 3 or 4 years, which allows people to write an article that basically says, here is the piece of software that I wrote. Here's what it's been used for. Maybe you'll have it be useful too. If you end up using it, please cite it so that I get some academic credit for it, some recognition of the impact of my software. And so this paper, this particular journal, it's been going on for a couple of years. There's about 1,200 articles in this paper, and they're all pieces of software, okay? Either libraries that people have used, not all of them are Python, about half of them are Python, half of them are R, but some are C++ or Fortran or Julia or Mathematica. It's the rules of this particular journal is whatever it is, you have to have made it open source. The code has to be available. So if you explore these papers, right, what you can do is you can see that there are 1,273 papers in the archive. 183 of them are currently under review. And this particular journal does everything in the open. So I don't know, let's just pick one. Okay, lattice symmetry. Okay, so eight days ago, someone submitted this piece of software for review. It's brand new, no one's even started it yet. If you go over to GitHub, that's where they have actually shared their paper. Okay, so you see they have in GitHub, and this is one of the reasons we're talking about GitHub. They have their code. Okay, they have their source code that they've written, and then they actually have the paper that's describing how this particular code gets used. Okay, so this is what a GitHub repository typically looks like for these projects, right? It's got a bunch of code. It's got a source, so you can go in, you can take a look at what the source code is. This one's written in the C++ language, so there's all the code. It's got some documentation on what it does. It's got some documentations on how to use it. This particular code is written in C, but they've also written a Python API to be allowed to use it. So it's an example of Python wrapping some code. You got some instructions on installing it and running it. And they've given you a paper, and they're going to review this and think that this paper is appropriate. Okay, for the purposes of this project, what I've done is I've gone through these 1,273 papers. I looked for papers which were mostly Python-based, but a few other things that all involved calculating or computing or analyzing something. They all have the general model of taking some input in and producing something out. And what I did is I took those lists of papers, and I threw that up. And so step one that you need to complete is I need you to choose a product topic. Okay, so my source information was just recent Journal of Open Source Software papers, and I made a list. Okay, so here's my list. This is my recommendation or my requirement for spring 2021 for this project. I want you to choose a paper from the Journal of Open Source Software. And I went through like 700 of them, had a short list of about 60, and I narrowed it down to 24 things that would do it. Okay, they are often from astronomy, oceanography, seismology, Casimir effects of physics. It may not be your branch of science, but that's okay. It doesn't really matter, because the point of this exercise is not the science per se, it's a computational workflow. So step one of this project is I want you to go through this list and take a look at some of these papers and identify something that tweaks your interest. Okay, so along the top here, what I've done is I just opened up all these ones. Let me show you a few of these papers. Okay, so these papers are short. Okay, all these papers are doing is an advertisement for the actual code. So Capitan, a Python-based linear potential flow solver. Okay, well, fair enough. That's a piece of code. Let me read this paper. Now, if you're familiar with reading papers, you know that papers can take a long time. Let me show you how short these papers are. What they have is a paragraph explaining what does this problem have to do with anything? What do we do? Well, what you're doing is it has something to do with what is called linear potential flow model. It's a model that describes interactions between ocean waves and floating bodies. Okay. Fundamentally, it's solving this mathematical problem. And if you've done fluid mechanics, you may recognize it. But if you haven't, you can just go, oh, okay, so this is a code which solves the problem, the scientific problem of how floating bodies interact with waves in such a way. Then it talks about the computational method. If you're going to use something called the boundary element method, which is a mathematical way of solving these kind of problems. And then a little backstory of where this code came from. Okay, so we've only read one section, and then it introduces a piece of software. It says, okay, the present work, Capitan, is a modernization of this code called Nemo, and it refactors it as a Python code. It's a Fortran code, which we've talked about a little bit before, a very high performance historic language still used, that's been wrapped in Python. You know how to use Python, so using this function allows you to call this function, and it's been cleaned up, okay? And it has a little bit of stuff here about how the code has been set up, and then that's it. It has an acknowledgement about who funded it and some references. So these papers are like 1 to 2 pages long. And what I want you to do is sort of just read the first few paragraphs and be like, hey, that's cool, or I don't care about this at all. There's no way I'll ever be excited about this. So identify something that looks cool and interesting. Okay, once you've identified a topic that looks cool and interesting, what I want you to do is look at the actual package. So, okay, here we go. Let's go to phase space. Okay, well, I'm just picking one. Here's something. Again, the paper is short. Okay, phase space. It's a summary. That's the beginning of the paper. That's the end of the paper. They're very short papers because the actual content is inside their software repository. So all of these papers have the following link. They have a software repository. Okay, so the software repository, if you go to the software repository, it has 2 things. One, it has a link to the actual paper that people use to write it, and it's got the code. Almost always, maybe not every single project, but most of these projects have some documentation in a README file, okay, that you can begin to read through. And my guess is this README and the Journal of Open Source Software paper is basically the same. It's got some instructions on how to install it and something about how to use it. Okay, so what I want you to do is sort of find this documentation and just get a sense of how would one use this particle. So, okay, well, this particle has to do with, it's called phase space, but it's the topic is high energy physics. Okay, so particle decay, particle colliders, right? High energy particles, think CERN. Okay, this is what it does. So what we do is here is a snippet of code which brings in a module from phase space, something called a gen particle. It creates some gen particles and creates some data. Okay, so this might be the computational step, the actual creating of thousands of events, right? Well, what I want you to do is I want you to create that data, save it to some file, and then open it up and do something with it. And the something with it could be a plot or a graph or something about it. Now, you're not a high energy physicist. You probably aren't. So you're like, well, how am I going to learn what to do? What am I going to do? Most of these things have documentation. You're looking for a directory called docs, and you'll see inside docs a bunch of these what are called RST, restructured text files. You can read them here, but what almost all these projects do is they're going to give you a link which is probably hosted on a site which is called Read the Docs. Okay, so not all these projects, but most of them have their documentation available and being rendered on a site called readthedocs.io. But behind the scenes, what's going on is this site is just going to GitHub, pulling up the documentation, and then giving you sort of a pretty way of looking at it, right? But there's a few other things in here. There's some documentation on how to use it. What are the calls? Now, some of them might be very simple. Other ones, let's pick pi oscillatory ODEs. I'm looking for some documentation. There's going to be almost always some examples in the documentation, okay? So these examples are ways people have used this package. So here we go. Here is a cosmology example from using this package, pi-oscode, okay? And we talked about notebooks. Here is a way of looking at how the pieces go together for this particular package. And my guess is my internet just died, which is why it couldn't load. Okay, well, that's a poor example. Okay, here we go. Here we go. Here is a little notebook, and all these projects have notebooks or some documentation that walks you through using the package. Okay, so this one's about the area equation. Okay, so the area equation, and you may have covered this when you did a math course at some time in undergrad. This is something you might want to solve. It's a computational problem. Okay, well, you can use the software, PyOS code, to solve that mathematical problem. How do you use it? Well, what you do is you define it. You define some solution, and you call this function. So this solution is the output. Okay, so this is the computational step. Okay? You've defined the function. You've done some processing. Here's the answer. What I want you to do is take the answer and save it in some intermediate file format, and then load that file back in and make a plot. So here is an example of a plot. Okay, so this is the exact solution superimposed with this solver. Right? When it comes to the plots, I'll get to the plots in a second, but you got to choose a project, something that takes some data in and takes some data out. Okay, so at this point, I said I'll always go back to these sequences, and it's okay. Today, the whole point of today is to talk about this project. So here is a list of project topics. So how about we spend like 15 minutes with you just clicking on some of these, and so I'll even throw this into Slack so that you got it nearby and right away. Just getting a sense of the scope and the kind of documentation and the pictures in the documentation of what some of these projects are. So you got an idea of what kind of scientific software I'm talking about, and then we'll continue on and look at the next one. You don't need to pick right now, but just look at, let's say 3. Look at 3 different packages that look cool. Spend 5 minutes on each, and we'll come back as a group in 15 minutes. Let's say here. So I'll just go to Slack. Okay, so I'll say this. Review about 3 of the project topics. Reconvene at well, it's 12:25, 12:40 my time, which would be, I hope it's 2:10. I think I'm doing the math right on that. Okay, Obid, you raised your hand. I don't know how you did that, but okay, great. What's the question?
I want to ask that we are just confined or limited to this project. For example, if someone wants to numerically model something like an body problem or shallow water equation, something like the scientific problems, is it any problem that someone choose another topic, or we are just limited to this topic?
Let's limit it to this list, because then I at least know that you got the data, you got the code. I know it's recent. It's something that someone else can find. If I make this open-ended, I found that people choose projects that just really don't follow this pattern. They'll pick some library, which is like a graphing library. So I'm hesitant to do that. So I'm giving you 24 options. Pick one of those. It's only a project. You're doing it for 2 weeks and then you're never going to touch it again.
Okay, fine. Thank you.
Yeah.
Hello, Professor.
Yes. Another question. Great.
So the question is, can you be very specific? What should we do? Like, should we re-implement these projects, or should we use these codes to do something?
You're going to use this code to do something.
Okay, just use their codes and do something and show it to you, right?
Yeah. So yeah, exactly. So again, and we haven't. We're still introducing the entire project, okay? And all we're at here is step 1. Okay, there's lots more to go through. We're only at step 1, and what I want you to do is just look through these titles, do a bunch of web searching on these read the doc sites, and find something that is interesting. Okay, and it doesn't have to be your final decision right now. Just pick something to work on for the moment, and then we'll go to step 2.
Okay, Professor, got it. Thank you.
Okay, sounds good. So I'll talk to y'all in like just over 10 minutes, and we'll go through what this means for each one of you. Okay, I think I'm gonna bring the group back together here. You may not have made your choice yet. You probably just got into it, but this is the idea. This is the research portion of the exercise where we're gonna pick some topics. So I just went through these things and I went, snow dunes. Snow looks cool. I don't know anything about cellular automata. Let's pick this one. And it's just a choice. It doesn't really matter. And you can change your mind if this one doesn't work out. A lot of the things will be sort of the same. So let's go as far. So this particular one I'll use as my example. You're welcome to choose the same one or something different. It does not really matter. Is all about simulating snow dunes. Snow dunes, I guess, are like how snow actually appears on the side of a mountain. And it has some model, cellular automata, and it does some stuff. Okay, so if I was doing this, what I'd want to do is I want to have gone to the software repository, identified what the code is, and as I said before, you're looking for a project that has some documentation, some source code, right? And then some examples of just like what to do. So this one has examples of a snow cone sintering snow and dune growth by snowfall. Okay, a snow cone. I guess it's just a pile of snow. And seeing what happens in it. Okay, so once you've got a project, and as I said, go ahead and change your project if it isn't working out. What I want you to do is perform at least 2 computational tasks based on your project topic. And then once you've done that, produce at least 2 visualizations of that report, and of that computation, and put it all together in a LaTeX-based report. Okay, so that's the overarching structure of it. The very next step I want you to do, though, is create a new public GitHub repo for this project. And I want you to name it CMSC6950 _project. And so that's going to be your project for the course. So right now, everybody can do this. It doesn't matter if you've chosen your project or not. You can do this. You can do this right away. Okay, so one nice way of doing that is jump over to GitHub. Okay, so I'll just go over to GitHub, like under my name. Okay, and I've got lots of repositories. All right, but what I'm going to do here is I'm going to, well, it's probably because it's short. I'm just going to go to my main page here, go to repositories, new, and I'm going to create a brand new repository, CMC6950 _project. Okay. Descriptions are good. Course project for CM6950 spring 2021. And I'd like it to be public because at some point we're going to do some peer review. We're going to take a look at each other's projects. It's always good to have a project that at least has a README file, and that's all I need. Okay, so we have a project, it's got a README file, and we're going to have a main branch all set up. We hit create repository. So there we go. We've now got this project. And what we're going to do is we're going to take that project and then clone it locally. Now, what I've asked you throughout this course is to always have some sort of terminal, some machine where you've got Git set up and installed. And what we're going to do is we're going to start to take that code, and we're going to make a local copy of that code. Now, you can use SSH or HTTPS. I think SSH is the modern way of doing it. So what you would normally do is you take the SSH string, you copy it, and you bring it over to a terminal, right? Git clone, and then we would type that in. And what it's going to do is it's going to try and connect to that machine. You have to ensure that whatever system you're doing this on, you already have an SSH key. So just to remind you that if you don't have an SSH key gen, just take the defaults are fine. Inside SSH, it'll produce a pair of files. An ID RSA, that's your private key. This is your public key. Public keys are okay to be public. You can show them. And then over in GitHub, if you go down to settings, and then within settings, you go to SSH keys. What you can do is you can make a new SSH key. Okay, and it's really just the contents of the file. That is what needs to get added. It'll want a password. And if you've already done this, this is great. But the point is, somewhere on this list, I should have this new key. It's never been used. It's for the purposes of reading and writing to from this machine. So I've now got that key. So if I go back to my main directory and I say git clone from here, I'm going to get a local copy of my project. Okay, so whether or not you want to think about your project as being this is hard to write, CMSC6950_project. Okay, it now lives both on GitHub, and you should have a directory in whatever machine you like to use called CMSC project, and it's got a README file in it. If you did a git status, you should see that you're on branch main with nothing to commit, and you've got a very simple README, right? It's just the name, the description. You know what? Just to confirm things are working, you could go ahead and you can maybe put your name into that file, do a git add README, do a git command, add my name, do a git push, okay, and verify that you sort of got this basic stuff set up. And now you can see that here, this is my README file. So that's the beginning. What this README file is going to do is include whatever you need to do to get the project software to run. So each one of these pieces of software has some instructions. And what I'd like you to do is as you're working on this, recording your readme.md, whatever you need to do to get it to work on your system. In addition, verify that whatever instructions you need are sufficient to get it to run on the server CMSC6950.monroelab.ca. So the README here is what you chose to do to get this to run. So this documentation for this Snow package probably has some information about how I get things working. Okay? It talks about dependencies and getting started. What you want is the subset of these instructions on what you needed to do to get it to work. It will not be exactly the same as these READMEs. This one, it's saying on most machines, the Python packages can also be installed using. I would like you to use a Conda environment to set your project up. Okay, so what does that mean? What it means is I want you to go ahead and create a Conda environment. So you could, I'll walk you through this with you. What we do is we just say, if you have Conda installed, and if you don't have Conda installed, we talked about this a little while ago, miniforge.sh, just do a Google search for it, download it, run it, and install it, right? You install it as a bash script, okay? And what it does is it gives you this command Conda, and Conda can manage Python installations. So what we're going to do is we're going to go into our project. We're going to go a Conda create, and we're going to give it a name. Now, it doesn't really matter what name it is. I would suggest that your name is whatever this package is, right? So this is called Rescal Snow. So let's call this Rescal Snow as the name of my environment, okay? And what this is doing is creating a place where you can install your own software on a machine that you don't have access to, that you don't have administrator privileges to. So it's going to put this in Miniforge. I'm calling it Rescal Snow because that's the name of the package. Yes, that's great. And it says, how do you use this? What you do is you say, Conda activate Rescal Snow. Okay. So now, once you're inside that Conda environment, and you see right here, what you have is the ability to install your own software. So we need to have NumPy, Pandas, and SciPy. Well, with Conda, you just say Conda install NumPy, Pandas, SciPy, and it will go off and download whatever code you need. So to make this work, we're going to need Pandas installed and Python installed and a few other libraries. Yep, that looks all good. And it's going to go off to the internet, download a bunch of stuff, and install it for me. So I have a basic Python installation. Now, so what I want you to do is document what you had done. So in terms of the README, right, you may have something like software setup, right? And you may say something like, well, what did I do? I said Conda create and what was it called again? I lost my name already. Rescal Snow, Conda install NumPy, SciPy, and what was the last one? Oh, Pandas. Pandas, SciPy, Conda activate, Rescal Snow. Okay, and we can put some notes here and say, assuming you already have a Conda installation such as MiniForge installed, right? That's sort of the instructions that I did. So I'm documenting this in a README. Now, there's a few bit of notation. So first thing you'll notice is I'm using my editor inside my shell. We talked about the importance of being able to use a text editor. You can use a command line text editor like I am. You can use Nano, you can use VI, you can use Emacs, or you can do this all in VS Code or in Atom or in Sublime, whatever editor you choose to use. If you've done some stuff with Jupyter, you might be familiar with this asterisk, this hash and double hash and triple backlines. This is all something called Markdown. And what Markdown is a very quick way of formatting a function so that it looks okay when just displayed as text. But if I add this README and I do a commit, add instructions for Python packages, okay, and I push. If I do it as Markdown, and I'll refresh this page, you can see that it's automatically rendering it nicely as like headings, subheadings, code. So Markdown is a really nice way of doing documentation on the fly. And if you're unfamiliar with Markdown, you know, a quick search on GitHub, Markdown cheat sheet. There you go. Here is like the quick version of how do I do headers, how do I do emphasis, lists, images, syntax and code highlighting, and you're done. And all I did is I just did a quick search on GitHub or on Google for a cheat sheet, and there's the summary. It allows you to do basic sort of structure for documenting things. So when you're doing documentation, Markdown can be a really quick and easy way of doing this. And what we're doing is we're building up an instructions on how we do things. Okay, so that's step one, is to get the software to work. Okay, so just to show you the scope of what we're doing, I'm going to try and do it here as well. It says I also need to have some machine dependencies. Now, anything with sudo, this might work on your computer. You don't have sudo privileges or administrative privileges on this machine. If there's any software you need me to install on this machine, just drop me it over in Slack and I will install it. So let's just leave this for now. Okay, it says you can download this software by cloning it or a repository with Git. Oh, okay. So let me do that. I'll copy that line. And what's it going to do? It's going to do a clone and it's going to go into that directory. So now I'm in a subdirectory called rescal snow. Okay, well that's fine. And here is the code. So this is all the same code that's up here. We just have a local copy of it. Okay, we got to get this project to run. Okay, now this is a C project, which means it's source code. We got to compile the code. Many of the projects that I've given you can be installed with a simple conda install and you're done. So this is one of the more complicated examples. A lot of them are simpler, where just saying conda install package name is going to work. So you might have an even easier case than this, but let's go through it. How do I install this software? Well, what you do is in a terminal, navigate to this directory. Okay, I'm in that directory, and run these commands. Okay, they want me to create a directory called build. They want me to go into that directory. Okay, I can do that. They want me to type in this line. Okay, now we talked about make. Well, we didn't talk about it. You watched a video on make. Make is a piece of software that tells you the order in which to compile software and do some sequence. What it's telling me here is I need to run this command to create the make file. So you copy the entire command. Now, if you were to copy this, copy and paste it, you're going to get errors, and you have to try and decipher those errors. This deciphering the errors is part of the learning experience that I want you to go through. So if you get an error like this, don't just throw your hands up and say, oh, it didn't work. Read what the error says. Okay, it says, no source or binary directory provided. Both will be assumed as the current working directory. Note that this will become a fatal error in future CMake releases. Okay, the current working directory. What is the current working directory? PWD, build. What's inside this directory? Nothing, it's empty. So that's the problem. It's just saying, I can't find anything for me to compile. And if you go back to the documentation, you'll hopefully see what the problem is. The problem is the command wasn't CMake go dev dmake build release. It was this double dot. That's the command they ask you to type in. What's the double dot represent? It represents the parent directory. So the directory where the files are in the parent directory. Oh, that's what I need to type in. Okay, so I type that in and we let it run and do its thing. I got another error. Okay, the nature of this project is you will hit errors. You need to try and solve them. You need to try and figure out what's not working. And it's telling you, I couldn't do this. I can't find PNG. Missing PNG library. You need at least version 1.6. Okay, so it's telling you that one of the dependencies isn't there. Well, that's what this line was telling you up here. It said you need to install this library. So this is something that you can't install. You might be able to install this with Conda, but if you find that you need to do it with one of these commands, on your machine, you should have administrator access. On this server that you shared, send me a Slack note saying, hey, James, can you please install the package libpngdev? And I'll say, sure. And I'll just come along and I'll log into this machine and I will say, sure, install it. It'll install the package. And when I install the package at a system level, I'm installing it for everybody. And so it's just updating that data. It's importing it. Okay, we now have that piece of software. And so I can go back to trying to compile this code. Okay, so CMake, what it did, it found the libraries. There's libpng. PNG is a graphics file format. It's looked for some other libraries, make sure they're all there. And then if you actually look inside this directory, what it's done is it's created a file called makefile. So CMake is a tool whose purpose it is to create a makefile. If I take a look at this makefile, these are all the instructions that generate my application. So the software is called Rescale Snow. The default target is all. And so if I just type in make, it will parallelize this and compile it. These are all the steps, all of the calling of compilers you need to make this program. Okay, so how do I do it? Well, I type that in and I just say make for J. What's the J mean? Adjust the number of cores. So it's actually going to build it in parallel and start compiling my software. Okay, so it's compiling all this C code and you're done. Okay, when you're all done compiling a piece of C code or Fortran code or C++, what you should notice is what you've created is a bunch of executables. These are the software. So these are the programs that I need to be able to run to do this project, okay? So any one of them, so there's rescal, right? /rescal. There, that's the snow model. It's a simulation of the snow surface model under the airflow, -H for usage. Oh, okay, there's a bunch of like command line options I can give it. This is the program. This is the model that does the work. Okay, so now that I've got it installed, I want to try and play with some of the examples in the documentation to try and get it to work, to do something. And as I'm playing with these things, what you're looking for is computational tasks. Now, depending on the project, what a computational task is might differ, right? For this one, it probably will mean running rescal with different parameters, right? That's what this program does. That's what the computational task is. For other models, it might be calling a Python function. So you'd have to write a script that loads in a module that calls some function. It might be downloading some data from external online source. It's something that uses the software, right? And you don't need to be original, though I will reward and be happy with novelty, as long as it's non-trivial, okay? It's got to be something that actually works. It has to do something. So you go through and you try and find some example in it. So here is a piece of example. Here is a tutorial. Okay, tutorials are great. Getting started, I've already set this thing up. And you can see that this person's documentation says, we assume that you have familiarity with bash and terminal commands. Our favorite is the Unix shell from Software Carpentry. In fact, you've already worked through that because that's exactly what I use for this course. I don't know these people, but they're doing it and thinking about it the same way we did. Rescal is designed to be run through a terminal. Great, we got a terminal. So here's what you do, okay? So you typically have some code which you need to run. This first test simulates a conical dune shaped by a strong wind. To run the example, go to scripts.snowcone.run. Okay, well, let's try and figure out what this means. Okay, well, if I go to the directory, you see that there is a path called scripts. Inside scripts is a bunch of examples. Well, the example they want me to look at is snowcone.run. Before running this code, let's actually take a look at snowcone.run. Okay, it's a bash file. We've learned about bash files. It's a sequence of statements we want to be able to run. What does it do? Oh, it does all the compiling for me automatically. Well, that's sort of cool. And then it runs this program called Genesis. So how do we run it? I've got to run this Genesis file. Okay, that's sort of neat. And then I run this program called rescal, and it does something. Oh, okay, that sounds good. Let's just try it. Just see if we can make it go. It's going. Oh, this command will take a few minutes to run. Oh, okay, it did something. So that was a computational task, right? You ran a command, it did something. What was the command you actually ran? Well, really, this script file is what you need to do. Here's all the steps that you need to run. You need to generate some binary cellular space. You need to call rescal. That's how it works, right? All the parts all the way together. Nothing happening. This is a good sign, right? It didn't crash, so it probably will run. It took a minute or two. Now I want to take a look at what this thing. Okay, now it's gone and produced a bunch of PNG files, right? So that's an image format. So this is one way of looking at the output of this model. What this code did is it rendered, this is the output, these image files, okay? So what they did is, to help you, is they've generated these images, and it's one way of looking at the output. Okay, well, so let's try and look at it. Now, I'm in a terminal environment, so I need to somehow open up these images so I can just begin to explore with them. This might be a good time to do something within Jupyter Notebooks. You may just want to open up your file system or do something else. I'm on a remote system, so I don't have the ability to very quickly look at these files as images. Now, what I could do is I could open up another shell, identify what the path of one of these things are. So I will say, okay, that one. And I could copy from my remote server, 6950. What's the directory? Well, it's this directory / scripts. There's the scripts. So what's the file name? Well, let's just grab this one. I could copy that file to my local machine. And on my local machine, I could maybe run a file browser and open it up and take a look at what I got here. Okay, good. I got a picture, right? That is a rendering of the output. And what it's supposed to represent, I think, not knowing much about this is a pile of snow. This is the top view. This is a side view. And what you're supposed to see is seeing a pile of snow growing in time. Okay, so it's worked. It did something. The output is these PNGs, but that's not the real data. The data are all of these files, these CSPGZ files. That's the output for this particular thing. Okay, so now I have some output. I'm like, okay, I ran it. So I probably can vary it by taking a look at snowcone.run, looking at the parameters, and it's probably controlling things like whether or not there's a wind or how fast the snow is falling. And there's a few other examples. So I could play with these examples, just getting a sense of how these things work and what they do and how to make them work. And what I'm getting as output is a list of PNG files. But the point is, what this program is doing is producing these outputs. That's the output. Okay, so whether or not you ran this Genesis and Rescale thing twice with two sets of parameters, you can figure out what to run by looking at this script and modifying it and making your own, or making two, or making a script that takes command line arguments. Do something so that the act of running this program is to create some output. Okay, and this represents your output. These CSP files, that's your output in whatever file format this thing is doing. Okay, so now we've got it running, and we've got some basic data, and it's giving you some examples. Okay, the next step, once you sort of got it working and running, what I want you to do is, so after you've identified these computational tasks, I want you to develop at least two visualizations of the output of this task. Okay, now in the documentation, there very well may be code that says, here is how you do something to make a plot. I don't want you to just find code, copy and paste the code and say I ran the code. I want you to sort of maybe look at the final picture and try and figure out using matplotlib how you can make a plot of the data. Now, we're not domain subject matter experts, so maybe the kind of plot you make is appropriate or not appropriate for what you've done. It doesn't really matter. Just pretend you're trying to make a plot of whatever you're trying to make a plot. The goal is to demonstrate to me that you've got some mastery of matplotlib. So you need to be able to load in this data and visualize it. So a visualization could be a plot like axis labels, dots on a page, a scatter plot, an image. Your plotting program may just recreate this image, right? Maybe this image with some axis labels. You want to just recreate this plot. How would I do that in Matplotlib? You've got to try and figure it out. Now, as you are developing this image, you may, what you're going to want to do is you're going to write this with Python. You may decide that the easiest way for you to work with this is to do this in a Jupyter Notebook environment, right? You want to play with it. You want to see what this file is. You don't know what the script is going to do. it is okay as you're doing this exploratory part of it to go ahead and create a notebook in Jupyter and run it locally or on this remote machine, however you like, to sort of play with it. But know that eventually, what we want is we want a script, a Python script that loads in this intermediate data and produces a file, a PNG, a PDF, some output file that does it. Okay, so there should be a command line argument, something where you say Python make snowplot.py snow 00019t0.csp.gz snowplot.pdf. Okay, you want to write a script so that eventually something like this works, so that it does something. Okay, now I don't have a file there, but we can start to build up something like that. Okay, so what we're doing is two things. You're coming up with computational tasks that use the software, figuring out how to make it go. Okay, and that might require writing a little bit of Python code to import a module, set something up, and make it run. It's totally okay if you're just taking an example or from the documentation and you're just trying to get it go to yourself, because getting the software to even run is an achievement. These are usually good examples of other people's software, but they're other people's software. And that's the reality, is it takes time to make these things go. So figure out how these things are called, how they work. Remember that anything inside of this subdirectory, this rescale snow, that's someone else's code. I don't want you to be adding this directory to your GitHub repository. If you need that repository to be done so that someone else can run it, add those instructions to here. So your next thing might be clone the third party just means like not yours, the one software repo. Okay, so how do I do that? Well, what would I type in? Git clone, and we want to make a record of precisely what is needed for someone else to redo what you're doing. So if what you need to do is you need to, wherever my button is, I've lost it, code, HTTP, right? Right? I needed to do this. I need to go cd recount snow, right? I needed to say make dir build. I needed to type in cmake, now whatever the line was, but it's whatever you're expecting someone else, and by the someone else, I mean me or one of your classmates. What did you need to type in to make this all go? Right, we needed to do that to install the software, and then you need to compile it. Okay, and once you have that documented, someone else can come. Oh, that's wrong. Someone else can come along and redo those steps. It should work on your own machine, but it should also work on this shared server that everyone has account to. Someone should be able to come along, do these instructions, and reproduce your project. So inside this directory, you might have a readme.md. Let's add that and update that to the to it. Add instructions to compile rescale snow. Okay, so that's done. And then I might start to make some scripts, right? I know I need a script that says make snow plot.py. Okay. Oh, not git. vi make snow plot.vi. Okay, well, this is a little Python program. Okay, well, we know how to do this. If name equals main, okay, that's fine. I want to run this main routine. Well, that's okay. I need a main routine. Sure, it's going to have import py matplotlib.pyplot is split. Okay, we need that. You know what? It's just going to be a clit.savefig, snow plot.pdf. Okay, so there is a script. Oh, there's no module name matplotlib. Okay, so here we go. I have created a little stub file, a dummy program that's just supposed to be a stand-in for making a plot. Okay, and I'm getting this error. It's saying no module name matplotlib. Well, I'll ask the group this because I've been talking for a while. But let's imagine you're doing this along here and you encountered this error. How are you going to fix it? What's the solution when Python says module not found?
Does it basically mean you just haven't downloaded the package yet? Is that correct?
That's correct. That's correct. So, okay. So Brad put in the things, a suggestion, and I'm going to say no, because you do not have system level privileges on these machines. Okay. So I'm going to actually go here and work if you do not have admin on a system. Okay, so that apt install bit, I want you to get away and not think about installing Python packages at the system level. That is a way of installing software, and yes, it's an option. It's just a not very portable method, and it's highly dependent on, and it can mess up your Python is used everywhere, including the operating system use it to make it run. When we're doing these computational projects, sometimes we want a different version of Python or a different version of a library than what our system uses. So using Conda is a way of insulating your environment. So these modules are local to this project. I talked earlier about Conda. Conda lets you install packages. So if I do a Conda list, I can see that here are all the Python packages that have been installed. And specifically, all with Conda info, all of that software is being installed in Home, JMonroe, MiniForge, Environments, Rescale, Snow. So anything that I install is in a directory that I own and won't conflict with anything else. How do you install it? Conda install matplotlib. Okay, Conda goes off, and it's very much like apt is for Ubuntu, but it works on Windows, it works for Mac, it works on all branches of Linux. It's not specific to an OS. It goes off and it finds the libraries that are needed to make this program run. Okay, so it's trying to figure out, well, what software would I need to download or install to make matplotlib run in this environment? Okay, and that turns out to be a computationally hard problem because they're looking at all the different versions and trying to make sure that we're up to date to get you the right versions. But something like this would work. Once you have solved the environment, thanks very much. Once you've been solved for it, and I'm just wondering if it's other people using it. There you go. It's saying this is all the software that needs to be installed to make matplotlib work. And you go, okay, that looks good to me. Yes. And it's going to download those packages. But the difference here is these packages are being installed into a directory that you have ownership of. It's not being installed in the whole system. Okay, it's installing whatever software is needed, but it's local. And that means you can run this on any computer, a high performance computer that you maybe aren't an administrator on. You can install software that might conflict with another project that you're working on. It's very rare that someone's ever working on one project, right? We work on lots of projects all the time. How do I have different versions of the software not conflict with each other? Package management tools like Conda solve that problem. It's not the only tool out there, but it's a really nice one in terms of working with the Python ecosystem. Okay, so it does take a moment, but once we're done, we're done. Okay, so if I go to Conda list, I've got a list of now all the software that I have installed as part of this package. And one of them is Matplotlib. Okay, so two things. One, we're going to check to make sure my plot works correctly. Python makes no plot. Oh, Matplotlib is building the font cache. This may take a moment. And I look at, and I have a function called snowplot.pdf. Okay, I know it's not the right data, but it proves that it's sort of working. Before you leave this, remember that you change your system. So go to your documentation and say, here is what you need to do to get this project to run. So I needed to do a conda install of SciPy, of Matplotlib. Add that in to your documentation so that someone else doesn't hit that error. Tell me exactly what you needed to do to get your project to run. That's what needs to go in this README. And then what we can do is we can add the README, and we can add snowplot, and we can make a commit, right? Add Matplotlib and a stub function for making a plot, okay? And it just starts to build up what's inside of this directory, okay? Now, okay, so the idea here is you're going to write some code that's going to do the computational task. You're going to write some code that makes some of the images. Again, if you want to use Jupyter Notebooks to aid you in doing this, go ahead. Two requests. One is your final project can't be a Jupyter Notebook. It has to be a sequence of scripts. And number two, include in your Git history those notebooks. What I want to see when we go to your project, okay, when we actually go along and we jump to J. Monroe at whatever it is, CMSC6950 project. When we actually look at your repo, okay, I want you to be able to go to this history button and see the work that you have done on this project. Okay, so if you've done something to a Python notebook in Jupyter, commit that notebook so that you built up a history of what this looks like. What that means is you have freedom to experiment. You can try and do something that doesn't work out and always back out the change. You could try and do something a bit ambitious and then go a different path. It also means that if after working on this snow package for like an hour, you discover, I can't make this work. This is like useless. I have no idea what to do. I want to do a new project. That's fine. Keep using this same CMSC6950 project and just add history to it. If you want to switch gears and go to a different project topic, you are welcome to. Don't delete this project. I want to see the history of you building up this project and trying things, okay? Trying things is a lot about this project. It's not about number commits. We want to see the history of how you work with it, how you built it up piece by piece by piece. Okay, so as you're doing it, you're getting in the habit of git committing often. Every time you got a piece of code that works, you would git commit, right? You want to sort of build this up. Now, when you have a git commit, right, you know that some of the commands we use, like git status, show you things that are untracked. Okay, now this rescale snow is important, but I never want to include it inside my Git repository. So I might choose to create a git ignore file, a .git ignore, and put rescale snow inside that file. And what that will do is means that it will ignore it as one of the list of untracked files. So I will add that to my repository. Git ignore, not cap lock, git commit, ignore rescal snow directory. And we do that so that when you get status, it doesn't appear. Okay. What you want in your project is at any stage, you can get this get status to be clean, right? You shouldn't have any untracked files. You should be able to know that you've added something. If there's a file here that you think should be added to Git, go ahead and add it. If you're like, oh, snowplot.pdf, I forgot, I really need to remember to add that file. Okay, git add snow plot.pdf. No problem. Remember to do a kit message. Stub snow plot.pdf, right? Just sort of hang there. So when I do a git status, it's all there. But we also know that in this particular project, I'll just copy it here for the sake of argument. These files are what the intermediate files are. Okay, you remember we ran the program and it produced all these intermediate files? When I say git status, okay, you're seeing all these things appear. Okay, these are untracked files. Do not add intermediate data to your Git repository. Now, if the data was really expensive, you might archive it in some way, but typically we don't put data inside Git repositories. Git repositories work great for text files, small images. They don't tend to work well for large data. So we don't store this data in here. So one of the things that I would be doing if I was writing this project is, and this gets you to the next sort of step here in this thing. So we developed some visualizations. I want you to have a reproducible workflow that drives this calculation. And this is where the topic from Monday comes in. Makefile. This project has a makefile to compile it. I want you to write your own makefile. And one of the things this makefile can do, okay, so here's a makefile. The way that makefiles work, as we learned, is you basically put in a name for a target of what you want to do. So let's say the purpose of this command was I wanted to create snowplot.pdf. Well, what does snowplot.pdf depend upon? Snowplot.pdf depends upon make snowplot.py. If I change this piece of code, then I want to update this image. How do I actually run it? I say Python make snowplot.py. Okay. I might have another target. Okay. Another target we typically have within a makefile is called clean. Now, clean are what are called phony targets. I think that's phony. Phony. Let me look up. I don't want to spell it wrong. Rescale, build, makefile. It's a dot phony. Sorry, I'm just trying to make sure I get the right version of this. Okay, and a phony rule is basically something which isn't real. It's not trying to produce a file. You're just telling make that this is sort of an instruction. Clean. Okay, so this is something we want to do. So here's something we want to do to clean things up, right? And one of the things I might do is remove all the CSP and GZ files, right? What are those? Well, those are all these output files. I know that any file with this extension is something that I want to clean up. So if I say make clean, it will delete all of that output file so that if I say get status, I will see only the untracked file. Oh, wait, I forgot to add my make file. Git add make file, git commit initial make file, right? Just sort of a stub. It's there, get status. Okay, it's all clean. If I say make, it will do whatever needs to be done to make this snow file plot. Okay, but we know that the way this is going to work is you're going to do a computation task, and then that computational task is going to create some intermediate file, and that intermediate file is going to produce some image. So really, this make file, this plot isn't going to depend only on make snowplot.py. It's also going to depend upon some output file, some csp.gz file, okay? And again, I'm just going to go into here and take a look at what these things are called. Let's just pick one. Oh, where is the I? It's going to depend upon this file and this file, right? Here's the script to make the visualization. Here's the data that needs to be available to be able to make this plot, okay? So what you're telling Make is, here's what I want, here's what needs to be there to be able to make it, and here's the command to be able to make it, to actually do it. So if I try and run Make now, it's going to complain, there's no rule to make this target, okay? I don't know how to do that. So what you do in Make is you add in another rule with whatever needs to be done Nope, let me just yank the whatever needs to be done to create that file. Okay, well, what needs to be done? Well, there absolutely needs to be a program called rescale snow, right? That directory has to exist, right? There has to be some environment, some executable built. And how do I get this file? Well, we probably would run snowcone.rar, or we would run rescal, or we do something to actually produce that program. For the purposes of the demo here, what I'll do is I'll just go to ccal scripts. I will just copy that file to the local directory as a dummy. So let's go through it. When I run make, spelling error, rescale _ snow, rescale - snow. Yeah, okay, so let's see what happened. I copied this file to my current directory. Oh, and it's saying this is up to date. No, I want to make the image. I want to make the plot. Okay, so the way that make works is by default, it will do whatever the first target is, okay? So in this make file, the first target is this file. So that's all you want. A typical way of doing it is you put in a sort of a default rule, okay? Just a dummy rule that doesn't do anything. Again, it's phony. It doesn't actually produce a file, right? And maybe it has a dependency, okay? And the dependency is snowplot.pdf. Okay, so here we go. By default, I want you to try and create this file, snowplot.pdf. Make will go and ensure that this file is up to date and this file exists. If this file doesn't exist, then it will create this file. And so that's the sequence of what make is doing behind the scenes. So if I say make, it will go and run that program. If I say make again, nothing happens because this file is now up to date relative to the input file. The output is newer than the input. There's no need to do it again. If I do a get status, it's showing me the files that I have modified and the ones that are on track. Okay, well, always remember to do your git commits, git add make file, git add snowplot, default to creating the snow plot. Okay. Oh, I missed the -m for message. Okay. I do a get status now, and you see how I'm doing get add, get commit, get status. I'm doing that again and again and again. When you do those get statuses, pay attention to the error messages. Okay. If it says an untracked file, make the decision about whether or not you should really be adding that file, whether or not you should be ignoring that file, or make sure that when you say make clean, those files are deleted. So that if you do a get status, it's clean. The working directory, this working directory looks exactly like it would is if you were to pull down this data again from GitHub. And so what you're doing is you're recording how you set things up and the actual workflow to generate the output. So compiling things, running things, no, not compiling things, running code, running computational workflows, running bash scripts, running Python scripts, running matplotlib scripts, doing whatever you need to do to create this as your final output. That's what this make file is supposed to do. Okay, it's a reproducible workflow in the sense that if I go get status, okay, now notice my branch is ahead of main by 4 commits, so let's do a git push, okay? So I'm pushing it up to GitHub. I do a git status, okay? It's clean. My branch is up to date. This is my local machine. This is GitHub. GitHub has a copy of this data. I can now come along and completely blow away this directory, okay? Remove forcefully the entire thing. It is gone. I don't have my project. But if I was to come along here on this machine or any other and go to the project, go to code, grab that string, and then go to git clone project, it will download everything I need to do to rerun that project. So if I go into makefile, I go into the project, okay, you can see how all the files are there. And if I type in make, it's going to do everything it needs to do to redo this workflow. Now, it's saying no rule to make target rescale snow. Okay. All right, I didn't automate that. So maybe what you want to do is in makefile, add another thing, okay? Does that path exist? And if it doesn't exist, what you can do is you can say, okay, I think this works in makefiles. Wait, I didn't listen. Please please clone and compile rescal snow, right? Echo C readme.md for details, okay? So maybe you'll add that to your make file so that when you go make, oh, I probably did the kids rescal snow. There we go. Right? You see how it's telling you this warning message? It's saying, oh, I'm supposed to read the README. And what does the README tell me? That I need to have already done this step and done this step for this to work. So you don't need to automate the downloading of your file or the compiling or the installation. That should all be covered in the README. What you want is, assuming you have done everything that's in the README, okay. Oh, I have a mistake in my README. Where's make? Assuming you have run this and actually have the file and the output and whatever else you need. So we, and of course, this is stuff that you have to document. Snowcone.run. Right, and this is what I want you to capture. These steps, capture these things within either bash scripts or Python scripts, actual work. Okay, whatever it does. So those instructions of actually running it should be captured here. Okay, don't just copy a file. Actually have the code to run the program, so that when I run make, it will generate the intermediate files and produce any plots. Okay. So now I can go and I can see an up-to-date version. So that's the idea of a computational workflow. And you can test if it's working by blowing away your directory and seeing if you can start from scratch again. And if you can't, there's something you forgot to download. Go ahead and use this system as a testing ground. So have your code on your home machine and then have it up here just to see, does this work? And don't worry about blowing the code away and recloning it. That's always an option. There's a few other instructions here about ensuring having a clean target. You want to make sure that auxiliary files, .outs, .auxes, .logs, PYCs, they shouldn't appear. They're ignored. One of the things we're trying to get at in this project is a topic about reproducibility. And so just as an aside here, I want to jump over and show you this link from Lorena Barber's group on reproducibility. And there's a few documents out here, but this is a good one for summarizing what I mean. There is a problem in science. There is a problem in computational science. We are not very good at making our science replicatable or even reproducible, okay? We want to test things. Science is all about figuring something out and so that someone else can go and do it again. One of the movements that's within the open science thing, the open science movement, one of the sub-movements is reproducibility. The idea being, since that our projects are more and more computation, we should be able to at least go to a new computer, get our code from version control, and run it again, and it should give us the same answer. That is actually a very high bar to meet. And the reason is things keep on changing, okay? Imagine you wrote a piece of software that ran on a Windows 3.1 machine or an MS-DOS piece of software, and you've got the floppy disk with that code on it. And now I want you to redo that result. Here's the problem. Do you have a floppy disk reader? Do you have a machine that even runs MS-DOS or Windows 3.1? The version of the compiler you're using today is 15 years newer. Does your code not work with the newer version, but it work with an older version? Where is that older version of the software? Are there any third-party libraries that you need to download that you can't find on the internet anymore? Have you captured all of the information you need to be able to just reproduce? And reproduce is just like running the same code to get the same calculation to get the same answer again. It's a lower bar in computational science than something called replication. Replication is in science where I come up with a scientific result, and then somebody else says, well, that's an interesting result. Is that true? I better design my own study to test that hypothesis. And so they do their own experiment, and they come up with the same scientific conclusion. If they do, we say that the result is replicatable, right? When someone is doing a vaccine trial, right? We're going through the pandemic, people are looking at vaccines. I want to make sure that vaccine studies are replicatable. If I did a study with 1,000 people with this vaccine and I say it's 95% effective, someone else should be able to replicate that, as in run their own study with their own participants to find the same level of stuff. I'm not talking about replication, which was rewriting code. I'm talking about reproducibility, which is if you started with the same input data and you ran the same computational tasks, do you get the same answer? And again, at one level, you may go, well, that's obvious. We'd always get that. And the other level is no, because we have historically done a very poor job in capturing all dependencies of a computational workflow. We might capture some of the data or some of the code, but not the entire environment, not everything we need to do it. So here is a number of articles talking about the development of the ideas of reproducibility. Now, like if you look at the papers here, this is a relatively modern idea. Like reproducibility as a topic sort of appears in the mid-90s, early 2000s. Like I was done my undergraduate degree by this point. This is actually newer than when I went to undergrad for. But these ideas are coming out and out. And the concern is more and more science that's out there is unreplicatable and unreproducible. And so one of the goals of open science is to be able to make your results reproducible. And the reason we make them reproducible is one, you can evaluate whether or not it was any good. It also lets people build on your work, right? Currency in science is all about citations. I write a publication. I want someone to take my idea and then do the next idea on it and cite me back saying I did it. Reproducibility helps to be able to do it. There are limits to reproducibility. And so I'm going to just refer briefly to this DSM 2012 article, and there's a few others. It turns out that if you ask a computer to add a bunch of numbers together or multiply a number of numbers together, you don't get the same answer depending on which computer you ask or which compiler you use. The reality is, because of compiler optimization, when you get two floating point representations of a number and you put it into a CPU and you say, what's the product of that? Depending on the order in which you do the operations, even though mathematically they're going to be identical, CPUs do not give you the same exact to the bit level of reproducibility. It's the architecture of the CPUs come in. Compilers make certain assumptions. They're approximately the same, but they're not the same at the bit level. The only way to truly reproduce a numerical simulation is to take the physical hardware that you have, as in the box, the screen, the monitor, the keyboard, the fans, the actual thing, put it on a shelf, leave it in a locked room, not connected to a network. Now you got a hope of being able to reproduce that computation precisely. People go through a lot of effort writing their codes so that they are reproducible between different numerical systems. I'm not even going for that level of reproducibility. I'm okay within precision. I'm just going for the idea of, have you captured enough of your workflow so that someone else can at least come up with the same figures, graphs, and plots as you did using the same steps? So this article talks a little bit about the motivations for reproducibility, what we mean by it. There was a bit of confusion over the last 20 years. Some people call reproducible research replicatable and replicatable research reproducible, but I'm using it in this sense of reproducible means coming up with the same output given the same ingredients, the same code. Replication is writing a new code to come up with the same scientific answer. It can be confusing between what you do it. So if you're interested in the background and the context, you can refer to this blog post as some sites. This is what we're talking about in terms of reproducible research. For every result, for every plot, computation, whatever, keep track of how it was produced. So if it's a script that did it, write down what the script was. Avoid manual manipulation steps. What that means is, if it's a GUI and you've got to click the button here, be worried. Really be careful when the step in your science was open the file in Excel and edit the rows by hand until they look right. That's a manual data manipulation step. Those kind of steps where someone is copying and pasting with a mouse and a keyboard into Excel is a major reason why science ceases to be reproducible. There's no way you're tracking 100% of the things that you do. When you talk about versions, okay, it's not just I used Python. It's I used Python 3. I used Python 3.8.2. I use this version of the library. I use this commit level of this Git repository. Version control. All these scripts we're using, put them in the version control, which is what I've been trying to encourage. Record intermediate results, okay? So save those files or archive them. Use standard formats. Don't invent a new format, right? If you have a randomness function, often when we're doing simulations for random number generators, there is a seed, a way of initiating the random numbers. You can imagine running a program that has a random number generator. Use a random number generator seed so that you can actually reproduce the exact same sequence of random numbers. That's a way for someone to verify, or you to verify, what your program did. Don't store just the pictures, store the data. And there's a few other things in terms of how these things work. So these are some principles that the open science community has come up with that allow us to do good science. And in some ways, these are just the extension of what we as scientists over the last 200 plus years have come up with about doing good science, right? It's just the extension of how these things work. So if you're interested in that kind of work, you can read this blog post, or you could just ignore this blog post and do this as the purpose of the project. But that's where I'm coming from with this information. Okay. Well, I went and I closed the document. That was silly. Okay, let's get that back. Oh, so tiny. What do I do with it? I close my image. Okay, so what are we up to? Project instructions. Okay, so you've chosen a project, a topic, and again, you can go through a couple of them and sort of find one you like. You can choose a. Just making sure. Oh, yeah, good. There's no messages down there in Slack. I want you to choose some visualizations. Again, you can use documentation to inspire you to come up with a visualization, but I don't want you to just copy and paste it. I want you to come up with your own Matplotlib-based visualizations. Try and be a little bit creative or explore some feature of Matplotlib while necessary. You need to be able to know how to make simple line plots with axis labels, but that's not really very ambitious. That's not really demonstrating that you've really tried to explore the scope of this visualization package. At least try to do something. You got to have a reproducible workflow, so use a makefile to make it go. And finally, I want you to take your results and write me a LaTeX-based report that describes what you're doing. So this report, it should describe the scientific software that you're using, what the problem is. It's really just reworking the same content as was in the Journal of Open Source Science paper, right? What are we studying? Very high level is fine. Like you can say, I'm doing astronomy and stars are bright. Like it's not a science paper. I just need to have some stuff that convinces me that you know what kind of science this is about. Describe in words what your computational tasks are, right? What have you actually done with your code? What kind of problem did you simulate? For my snow cone one, I would say, we want to look at growth rates of snow cones, of snow piles under different levels of wind. Okay, so I ran this program and it simulated it. Tell me what you simulated. Tell me what you did in words. Include in that LaTeX document any of the visualizations that you made. And your report has to have a bibliography. And at minimum, that bibliography is going to have one entry, namely the JOS reference, right? You want to include a BibTeX bibliography. Now, your makefile should have a target of report.pdf, and this should be the default target. Okay, so I want to talk about this for a second. I'm hoping that you had a chance to watch the video on both Make and LaTeX. So let's take a look at this thing, makefile. The default one I want the default to be something called report.pdf. So at the end of the day, what we do is we go from a report.txt text file and any of the required plots that are required, and then we do whatever needs to be done to actually produce this report, okay? So if you need to also do a BibTeX in there or anything else, okay? Or if you need to call this again after you've run it, if you're familiar with LaTeX, you sometimes need to call it a few different times. Put whatever commands are needed to make LaTeX do its thing and convert this into that. So if I try and run this, it's going to complain. It says, I don't know what report.txt is. Okay, now, some of you might be LaTeX people, and some of you may be going, LaTeX sort of new to me. I haven't done this kind of thing before, but that's okay. So here's what we can do. Okay, I'm going to add to makefile. I'm going to commit this one. Commit add report.pdf to makefile and push it. Okay, so I've got it up here. It's now on GitHub. One of the tools you can use to help you doing LaTeX is a piece of software called Overleaf. You don't have to use Overleaf, but it's available and free, and you know, some people like it. It's an option. Okay. Overleaf is sort of like a web-based environment. I talked about this in the video. It's like Google Docs, but for LaTeX. Go ahead and create a new project, but in particular, take that project and import a project from GitHub. Okay. So I want you to link your Overleaf account with your GitHub account. Now you might need to go into account settings and set this up. There'll be some sort of validation, GitHub integration. You're going to have to link that in so it knows about it. But if you go to new project and you say import from GitHub, okay, it'll give you a list of all your GitHub repositories. I use GitHub a lot, so I've got a lot of projects, including all of yours and everyone I've ever done any work with. So I don't know even where mine's going to be in here, but there it is. CMSC6950 project, import to Overleaf. Okay, so what this is doing is it's making a Git clone of that product inside this thing. So these files are the same files. And what you can do now is you can create a new file. Well, let's call it report.txt. Okay. Okay. That's what it is. This is a basic, simple piece of LaTeX. Okay. And the idea is document class. You want to have a report. You want to have a beginning of the document. You want to have an end of the document. You want to have a title. CMSC6950. What do we call it? Rescale snow. There we go. That's the name of it. You need to have some sections. You need to have an introduction. You need to have some sort of results, text about software package. You're going to want graphics X. You're going to want some images, right? Include graphics. What do I want to include? I want to include my snowplot.pdf. Okay. Let's see. Whoa, I did all that without any errors. Okay, you can see I have the beginning of some code here. I'll do a make title, recompile. Yeah, there you go. There is a nice beginning of actually, you know, it's not use report. I know it's a report, so we're going to call these articles. There you go. So now you got an introduction with some stuff and some results and some stuff, and you got the beginnings of the report. Now the idea here is you're using Git to interact or share stuff between it. So remember that you have the full history. I need you, as you're writing this, every once in a while, it could be after you completed the section or maybe every day or whatever you want. You want to take that data and you want to do a submission. Okay, you want to do a commit up to GitHub of that. Switch to the main document before competing. Okay, so there's a bit of configuration we have to do here. Somewhere on menu source. No, I don't want the source code. I have the sync. Documentation, and this is where I'm drawing a blank here on. There's my project. There's my project. Oh, rename. Copy. Oh, main document. Report to text. Yes, yes, it's there. It's all good. No, I don't want to submit it. Oh, take it. Submit means actually like submit to a journal. Wrong idea. But what I want to do is have these things. What Overleaf is doing for you, I think, is you don't explicitly get to do any commits. I think what's going on, let's just find it out here for a second. J Monroe, my project. No, it's not there. How do I save? We obviously got the data. We keep on changing this. Oh, sync, GitHub. Here you go. There we go. It just took me a second to find it. Okay, so if I go to the menu and I go to sync to GitHub, this project is synced with things. What that's going to do is download any changes and push any changes from Overleaf up to GitHub. So I click on that button and then I click push Overleaf changes to GitHub. And I want the commit message. Okay, initial report file, just because I have a dummy, right? I want you to do this this committing, right? And it's this action and Overleaf menu, GitHub, click. That's actually doing a commit message. Once you commit it, if you jump over and you take a look at your project, I'll refresh the page, you should see there is now a report.txt file in your project. You are welcome to use Overleaf to help write your LaTeX because, you know, it just renders it, allows you to see it really quickly. But the idea is you should also be able to go over to your command line, do a get pull. Okay, you see how report.txt got added, and then type in make, and it will generate the entire report. So now in this repository is a report.pdf. Okay, again, git status. This should be cleaned when you're all done, right? So if I do a make clean, it should delete this file, and this file. And that file really should be part of the repository. I want to keep that. So what I'm going to do is say git add report.pdf, and I'll commit it. Save report.pdf in repo. I'll do a push. And then you can jump back over to your project and do a refresh. And now you have in this directory your report, your PDF as part of this thing for anybody to be able to see what you have done. And there it is in nice, beautiful LaTeX with some plots, all that kind of stuff. So what we're doing is we're building up a reproducible workflow using a computational program as the engine, and it almost for sure is going to be Python, though it doesn't have to be. It's one of the 24. You're demonstrating your ability to put these things together using Makefile and Bash scripting. You're demonstrating your ability to do a little bit of Python, importing functions, making functions, calling things, writing matplotlib-based visualizations, and you're demonstrating your ability to create a PDF output all the way through. So this whole thing becomes your project, right? It along with its history, right? And you can see how we've got this history of all the stuff that's going on, both the commits from Overleaf and anything else that I did. So there will be a fairly long list of commits when you're all done. Okay, we are on the final step here. Remember that I am looking for scripts. Could be a Bash script, could be a Python script. Notebooks are fine. You could have some notebooks, but they're not part of the eventual workflow. So you need to have standalone scripts that are driven using Makefiles to make it go. I would like your projects to be pushed up to GitHub, okay? And what I'm going to have you do is name your project, whatever your GitHub ID is, CMSC6950 project. That will allow them to be discoverable by each other. You obviously can't just reproduce what someone else has done, but it might be helpful to look at someone else's project going, so how hard are you trying here? What have you tried in your project? You have now seen me build up this initial one. This project is readable. You can see the parts of it. This is the basic structure of all of your projects, independent of what program you see. Yours should have all of those parts in it. Again, build yours up so that it does all of those things. Okay, now we're on to the last part, which is how we're going to evaluate all this kind of stuff. So what we're going to do, and this again is in 2 weeks, so you got to get moving on this, but this is like the assignment for the next few times, is the report should have a section which describes the project topic and the software used, right? Couple paragraphs. Do you even know what you were doing? Mark that a 10. Did you describe your particular computational tasks? Like does your report indicate what you did and how you set it up? Do you include a citation with a bibliography to the package? Are you clear about what parts of the package you're actually using? These packages can typically do 100 things. Which 2 or 3 things are you actually doing? Let's talk about the computational tasks themselves. Does it work? If I look at the documentation for this third-party software package, and I look at what you wrote as code, does it appear to work? Does it actually work? Does the code you wrote, is it readable? Is it understandable? Is it commented? Does it make sense in terms of using it? Are you using Git and GitHub, right? So is it available on GitHub? Does your Git history have a log of several different commits showing progress throughout the project? Are the commit messages meaningful? Messages like commit, 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 those aren't very meaningful. What did you actually do? Is your Git repository clean in the sense of, if you have a few old scripts that you didn't end up using, did you remove those from your repository? Did you delete files that really aren't meant to be here? The project should look clean and organized when you're all done. Ensure that the instructions that you need to set this up are in the readme.me, and make sure that once I've done the instructions in the readme.markdown, if I just clone your repository and I say make, it does anything and everything that is needed to generate report.pdf. So if I delete report.pdf, I should run your command and be able to come up with it. I should be able to delete any one figure, and only the code needed to regenerate that figure should need to be rerun, not everything. So run this all the way through. There's a little bit of, are you using LaTeX correctly? Do you have at least a section and a make title and include graphics? Okay, and that's a bare minimum. You probably want a bit more than that, but at least that. Are you using matplotlib? Do they have decent styling options? Do you have axis labels or legends or colors? Do the plots make sense compared to what your computational problem was? So those are like the minimum requirements, right? So if you just do all of this kind of stuff, if you do up to here, that's like 75%. That's like a B. You passed the project. That's fine. But this is a graduate course. So I would like you to take this opportunity to push yourself a little bit in terms either of the things you were attempting or the kinds of program you are running, to sort of push it up from a B if you want an A, right? And so I don't know what to call this, but I'm calling this scope and effort, right? Did you do at least 2 computational tasks? Are there at least 2 visualizations? Are the tasks and visualizations appropriate for a graduate level course? Like, did you do something that took more than 2 or 3 minutes to do? Like, did you try? And this is a very subjective sort of one. And what it does is it just allows me to reward you when you tried something, even if it was hard, that didn't work out. Remember, I have your Git repository history. So you could try something and fail at it, and that's okay, versus someone who just did the absolute bare minimum of running the first example, and their plot is 3 dots on a page, and they're like, I'm done. Like, well, yeah, you're done, but not very impressive. You didn't really push the envelope or push your learning or demonstrate that you were trying to learn. So I'm going to call that scope and effort very subjective. Now, because it is subjective, I want some feedback from the rest of you on each other's project. So another component of the mark will be peer evaluation, okay? So what we're going to do, and this is what we're going to do on the last day of class, this is why this project needs to be done by June the 17th, is I'm going to break you into small groups, and within the small groups, I'll have you evaluate each other's projects according to these things. So I think there's 19 people in the course. 19 presentations is a little bit much to do in one day. But what I'm going to probably do is split this up into 3 groups, maybe 4 groups, 3 or 4 groups, and that will provide a peer group. And so what we'll do is within that peer group, someone will give the presentation of whatever their topic was. Everybody else will look through the report, look at the code, and try and just evaluate these things going, did this person do something that was cool or like not so cool? Relative to the other people in the group, and just give me a mark. We'll call that peer evaluation. So that'll go into it because I want you to look at each other's things. So we'll spend about half an hour per project on June the 17th. Again, within a small group, so I can actually get through everybody. And I'll pop in on each one of those small groups. And then I've got another section which here on originality and mastery. Again, this is just to decipher between a project that gets a 90% and a project which gets a 99%. Did you just do the examples as writ directly, or did you try and innovate how the use of the project? Did you demonstrate use of bash scripting or data structures or functions or matplotlib or numpy or pandas or something in your code? Did you do something which is interesting? And again, highly subjective, but this is just trying to separate out the very good from the excellent. That's sort of use. And what we'll do is we'll just take those 10 parts and we'll just use a rubric of like 0 if you didn't do it, 3 or 4 if it's really satisfactory, a 5 or a 6 if it was like, hey, you tried, right? So if you did one of the 2 computational tasks, you're in 5 or 6 territory. 7 or 8, you did everything, but it sort of was lackluster, or you did it, but you really didn't demonstrate that you were writing Python code, or you were using Make, or you were using Matplotlib in any sort of non-trivial way. A 9 or a 10 is like, yeah, not only have you done it, but you've done it in such a way that I and your peers can recognize that this is a graduate level project. So again, that is subjective. It's just trying to separate out the B's from the A's. My expectation is everybody will be in this category. I'm just trying to figure out whether or not you made the leap from here to here. The projects up to this, the assignments up to this point have been are as usual very well done. The marks are very, very high. So you're going into the project with a very high mark. At the end of the course, my expectation is everybody's going to come up with at least a 75, if not an above 80. That's normal for a grad course. Just trying to figure out which 95s and pluses do I need to assign in this course. That's what I mean by these things. Okay, so that was a long introduction to doing it, and my hope is by watching me begin to do some of the projects. Okay, so I'm doing this in a terminal. I'm downloading software. I'm trying things. I'm trying to make it go, and recording within Git. That's the idea. Look at a few of these different papers, and specifically the software repositories and the examples, and pick one that you're like, that's cool. Try it, okay? And when you go to actually get it to install, okay, some of them might be easy. It might be as simple as, let's find the documentation. PyAutoLens, I don't know what it is, installation guide. Right? It may be as easy as saying, oh, here we go, conda create, we talked about this before, AstroPy, NumPy, NumPy, those are the dependencies, and then use pip install to actually install some other dependencies, and then you do the cloning, right? So this might be the sequence of steps. You might want to, in your README, have that exact sequence of steps. That's setting up the software. Go through this, get it installed, and then do the tour, okay? How-to lecture, gravitational lensing. I don't know anything about gravitational lensing. Hey, there's some Jupyter notebooks that explain how this works. Oh, the tutorials. Tutorials are good. Oh, there's tons of stuff here. Well, you're not going to do it all. You're going to pick something in here that looks interesting. Ray tracing. I say ray tracing is fun. Okay, here's a tutorial. Ooh, it's going to open up a binder. A binder is a way of running Jupyter code on an ephemeral machine. So here is a computational task, and he's explaining what he's doing. This is how to actually make it load. Here I've got a grid. I don't know. Let's run through this. Let's see what happens. I've never run this one before. Okay, so it's configuring this stuff. It does a lens. Okay, I don't know what a lens is. Here's some tracers. Ray tracing. Hey, it's tracing some pixels. So this tracer image, this is the output, okay? So this is what you'd want to save to the disk in some file format. And then in this program, he's written his own A-plot tracer plotter program to produce some image, okay? Okay, so what you would do is you would take traced image. Okay, I don't even know what a traced image is. A traced image is an array. Oh, it's a NumPy array. That's all it is. It's a NumPy array, right? It's got a shape, right? And that data is being plotted onto this graph. Okay, so what you might do is take this array, save it to disk. That's a computational step. And then in your matplotlib visualization, yes, this command does it, but can you make this plot? Like using this data, can you figure out how to make a plot that does, well, this? And it requires some playing, right? You might go, okay, P color mesh traced image. Oh, I don't have that installed. Okay, import whatever it would be. Import matplotlib pyplot is split. Oh, value error. Oh, I need more images. Okay, I am show. Oh, reshape. It's the wrong shape. Reshape 100 out of 100. Ah, there you go. I got a picture. Okay, so I took me a little while, but I figured out how to create that basic shape. Okay, well, how do I do a title? Split.title image. Oh, okay. And what you're doing is you're figuring out how to make a plot like this, right? So that could be one of your visualizations, going, I just want to make this plot. Or there's some other more interesting thing in the tutorial that, okay, that's a cool plot. How do I make that plot, right? What these are is gravitational lensing, as in you look at something, but in between you and the thing you're looking at, there's this big punch of dark matter, and light itself is being bent. If you remember, this is sort of a thing, image of a black hole. You might have noticed this in the news about a year ago. This is our first observational image of a black hole, okay? And what we're seeing is the light bending around the mass of the black hole. So this is an experimental observation of a black hole. And incidentally, and this will connect you with what we're doing, if you actually look at what was behind this, how scientists actually calculated this image of the first black hole, they used telescopes, and then they did some processing. And if you look at the articles here in terms of black hole imagery, let me see if I can remember, because it was a year ago I read this. I'm pretty sure this data was all processed and done using the PyData software suite. It was done using NumPy and Matplotlib. That's what they did in this program. So what did NumPy do? Well, they had these satellite observations. They did some data correlation. They did some image analysis, and they spit out these pictures. Okay, this was using the software suite EHTIM. This is the piece of specialized software which was built on top of Matplotlib and SciPy, which is built on top of NumPy. So if this was your project, EHTIM would be the software that does the work, right? And so there's an example of a piece of actual honest to goodness science, which is being done. I don't know. I saw some talk by Katie Bowman who went over this. Let me just see if I can find her. News. I don't know. If you look up the story behind it in terms of how this stuff comes to be, all that original data on that image of the black hole, it's built on top of the PyData the stack, right? So you're basically being trained to do the kind of stuff like looking at black holes or whatever area you're interested in. Okay, so that is my big long spiel on what the project is, what the scope of the project is, and the kinds of things I'm looking for. I would encourage you over the next few days to at least make an initial choice of what project you're actually working on. As you choose your project, what I'm going to ask you to do is go to this project, CMC Project Spring 2021, okay? Go ahead and fork that project and edit this file that says projects.md and add in a line with your chosen project. Okay, so the way that a pull request works, you might have seen this, is a little bit different from Git, is this project is owned by me. I want you to fork this project. So this is the instructions, right? So you're going to go ahead and fork this. You're going to have your own copy of it. You're going to make a modification. You're going to add in a line, okay? So what do I mean? I mean a line that looks like James Monroe Rescale Snow is the project, and the link to get to that project is github.com, my GitHub address, CMC6950 project. Okay, and once you've made that change, okay, add in Monroe's project. So now in this list of projects, there is a new thing called Rescale Snow. And so now anybody can go to this list and say, hey, what's James doing? James has chosen to do Rescale Snow. It's okay if 2 or 3 of you choose to do the same project. You may also choose going, oh, everybody's chosen this one. I should really try and do something different. But the way to get your project into this list, again, is go to GitHub, go to Project Spring, fork it, and then inside that fork, make that change and submit a pull request back to me to update it. And at some point you need to change your project, go ahead and submit another pull request. We're going to use this file to do the peer evaluation at the end. So at some point, it's also a good way of me seeing which projects you're working on, and there are problems. But anyways, that's the project. Okay, I will stop sharing and I will stop talking. I said the whole thing today has been about getting the project launched. Questions? Have I made myself clear on what I'm looking for?
I think we understand everything, but I have one question. If I face
Yes.
any difficulties during the project development, can I talk with you with the difficulties? And can I ask
Yes.
you question? Okay, that's the
Yes.
thing
So
I
so
want.
so yeah. So there's two things. Like you could always send me a message in Slack.
Yes.
You can send a message on the general Slack because maybe
Okay.
someone else is doing the same project, right? The same software package. So definitely be public about this. I'm happy to go over your project, like just taking a look at it as it comes together, right? So if we want to spend half an hour talking about it next Monday and next Thursday and next Monday, we can.
Okay.
Right? You're not on your own, but I need you to try. And I know what will happen. You will try some software and you're going to get an error message. That's normal. That's expected. Okay. If you don't get any errors at all ever, you probably aren't doing something hard enough. Right? So try something. Do it until it breaks, and that means you're getting close to what we all do in computational science all the time. Now, I know many of you are computer science students, so you may not have a research topic which is like this, but you may end up being a software developer for one of these kind of projects. You may end up supporting someone who is doing this kind of work. These projects are written by practicing scientists. So one of the things you may also be curious to do is take a look at the code they've written and be like, how's this project created? Not always, but often the actual people who are the coders on these projects are practicing scientists. They are not professional software developers. So you may see things going, well, that's weird, but that's because they're trying to do science as opposed to do development for a company. So it's a different kind of code, but this is how we do science.
Thanks, Professor.
Okay, no problem. Anything else to discuss today?
Hello, Professor.
Yes.
Just a simple question. I know what I actually didn't get what the make file does. What is the use of it? Can you tell it briefly?
Yeah, I can go over what a makefile is again. So when you're doing what I'm going to call computational workflow, okay, you're running a program. That program's output is needed to make a plot. Then you got to take that plot and put it into a LaTeX document. It's a sequence of steps, right? The sequence of steps needs to be done in order. You can't make the report and then run the model or run the code. You got to do it in sequence. What Make is doing is coordinating the order in which you're doing things. What it gives you is Make is going to ensure that only the steps that need to be run are actually run. So you could imagine you have a thesis, okay? And your thesis has 85 different figures in it. And you make a change to one single figure. You don't want to have a script that goes off and remakes every single image every time you make a change. You want to put that into something like a makefile, and it'll go, oh, hey, the code or the data for that one image has been updated. So that one image file needs to be rebuilt. Oh, the image file got rebuilt, so I need to rebuild the final report.pdf. And it's controlling the order and the dependencies of the software. There are other workflow tools out there. Make is just a very common one in terms of how software is organized. So I've just chosen that one.
Okay, Professor, got it. Thank you.
Okay.
James, I have a general question about LaTeX, if you don't mind.
Sure, Mike, no problem.
So if we're publishing papers, typically you'll go through the peer review process. And then once you have comments back from editors and you have to make changes to, say, whatever document or whatever paid manuscript you're working on. So in terms of doing that with LaTeX, is that, I've written my first paper with Word, but in terms of doing that with LaTeX, is that fairly straightforward to do in terms of tracking your changes and making a new document so you can submit that to an editor? Or?
Yeah. So you know that it's really different domains of science, right? There's some domains of science where the what you edit are like Word documents, and that's what people use, and that's what you edit and you use. There's other branches where LaTeX, so chemistry, physics, mathematics for sure. LaTeX is the default way of how things are actually typeset. So when you're editing your document, you're going to edit them in LaTeX. But what you submit to an editor is rarely the LaTeX file. What you submit for review is the PDF. So when someone is giving you comments, the way that they say their comments is, on page 4, line 16, paragraph 7, I disagree with this. And so they're with an editor and the peer review process, people are rarely doing, they can mark up PDF files, but they're not marking up LaTeX files. So the descriptions are very much, you describe what line, what paragraph, what page you have an issue with and what your question is. And then as a response, when you're doing a journal article. Now, I don't know, Mike, have you published journal articles?
Yeah, I published 2 articles so far, and they've both been in. So.
Yeah, so you know that like as part of the review process, you get your reviews back, and then what you need to do is you need to write a response to the reviewers. Right? You need to say, okay, I appreciate your comments. Thank you, reviewer number 1, for your comment. Here's what I did to address it, and you explain what you changed in your paper to satisfy it. And then you go to, thank you, reviewer number 2, but I respectfully disagree. I think widget should be the color blue, and I'm not going to make that change. And then you submit that document, and the editor evaluates whether or not it is. But you're not doing track changes at a LaTeX level. Within your research group, within multiple authors, you may need to do some rounds of revisions. Those work just fine with LaTeX, because you're going to take LaTeX and a revision control system.
Okay.
Right?
Yeah.
Right. So you're not just passing the LaTeX file around. You're using some version control system, like Git, to handle who changed what and why. Yeah.
Okay.
There may be some LaTeX packages out there that do track changes the same way that Word does, but not ones that I've ever used.
Okay. Yeah, I was just curious because like the past 2 times I've done it, they've asked for a track changes. So where I guess it's, you click the button, it tracks the changes, and then it puts a bunch of red lines and things you eliminated, and then doesn't do it for the new stuff.
Yeah. So this is in LaTeX.
No, well, I guess what I was wondering is that where I'm familiar with doing that and where, but I guess this is going to be one of my first times using LaTeX. Can you do that with LaTeX?
Yeah.
Like, if I wanted to write a paper moving forward in LaTeX, can you still do that?
It's tricky, right? We probably could write software tools that would look for those differences. There are definitely LaTeX packages out there that can do that underline highlighting thing, but that's not typically the way you'd look at it. So if you're in a journal that uses track changes, well, that's a Microsoft Word shop. Almost for sure that's their workflow.
Okay.
But the reason, it depends what your area is, right? The reason people use LaTeX in the mathematical sciences is because we're not really editing letters and words, we're editing formulas and figures. And Word is terrible
I agree.
at being able to be explicit. Like, you can do a few equations, but it's not nearly as nice as it is in LaTeX.
Yeah. I also find Word can get slow depending on how big your document is, depending how big your thesis is, for example.
And lots of people write theses in Word, and it can be used, but it depends upon your research specialty, right? So there are domains where everyone uses Word and they wouldn't even think about using LaTeX. And there's other options as well. There's other typesetting languages out there in the world. So in fact, I talked about Journal of Open Source Software. If you actually look, the file format that Journal of Open Source Software uses is Markdown.
Okay.
So that's how an author submits their article as a Markdown document. And so you can do track changes in Git. And they actually use GitHub for their whole review process.
Oh, well, it's neat.
But it's a public review, right? So
Right.
you know that reviews are typically private and things like that. there's another way of doing it, which is saying, well, reviews are work. Why don't I get credit for giving my review? Pro and con, but you know.
Cool.
Anyway,
All right, thanks,
great
James.
question. Yep. Anything else for today?
Can I ask
Oh.
a question, Professor, regarding
Sure,
the template? Should be look like a scientific paper, for example, having an abstract introduction.
You choose whatever you prefer. If you want to, like I'm fine you just using the basic standard LaTeX article style. You are welcome to it. I'm just sharing my screen right now here. I'll just go back up. If you want to just go to a project lab report, here are, I don't know, 1,000 different report galleries of different styles. Pick whatever one you want. It doesn't matter.
Okay. Thank you so
Yeah,
much.
whatever you like. Because you normally, for a journal, every journal has their own style. And so you normally would use that journal's template when you're writing your software. Because some journals are like 2 columns, some journals are not. I don't care for this project. I just need a style, and it could be the default style. Whatever you think looks cool. Yeah.
Regarding the group working, a question: how many people can be just in a group? For example, 2, 3. How many is it?
Well, there's no limit. There's no limit at all. And you're not in a group, right? So like we talked about whether or not this should be a group project or not. Time zones are an issue. I can't get you all in the room at the same time. I wouldn't want one person being held back. The evaluation groups, the peer evaluation groups, we'll come up with that. I'll come up with that the night before, and it will just be random.
Okay.
And it will probably be 4 or 5 people in a group. But that's just to split it up so that you can review 3 projects within about a 2-hour window.
Okay, thank you so much, Professor.
No problem. Okay.
Okay, thank you.
Okay. Well, thanks very much, everybody else. I said on Monday, I've got a few topics on data structures to talk about. On Thursday, I want to talk about high performance computing. So I'll try and do about an hour. What will be the flow? I want to take up assignment number 7 on Monday. So I need, again, 2 or 3 of you to volunteer to discuss whatever your assignment number 7s are on NumPy and Matplotlib. And we'll do that again on Thursday. I'll spend about an hour and a half presenting some content on some topic which is related to this, X-ray, SQL, high performance computing are on my short list of 3 ideas for 3 lectures, but you know, some topic which I think is of use to many people. And then we can spend a bit of time just reviewing how the projects are going in our time. We've got 3 sessions, Monday, Thursday, Monday, and then the final Thursday, we'll call that presentation day for these projects. And that's the course.
I want to take this opportunity to just ready as a volunteer for assignment number 7, if it's possible.
What would you like to do with number 7?
I want to be a volunteer for the next session.
Okay. Remind me of that on Monday. That'd be great. I will. I said I have a shorter list. I want to get everybody eventually. So
thank you.
Perfect. Thanks very much for the volunteering. Okay, I will let you all go. It's been a little bit long. Have a great couple days on your weekend, and we'll see you on Monday.